Have you ever thought about what lies beneath your feet, not the dirt or the rock, but the restless motion underneath it all? The ground feels steady, yet it drifts, folds, and breathes on timescales far too slow for our eyes. Continents slide like vast rafts. Mountains rise, erode, and rise again. Deep below, heat and pressure reshape stone into something new. Every quiet field, every city skyline stands on a surface that never truly sleeps. When you look at Earth from that angle, calm becomes an illusion, and motion becomes the rule. If the hidden rhythm of our planet stirs your curiosity, a quiet like and subscribe helps more minds join the exploration. Settle in, we're heading down, beneath the restless Earth. Beneath every step, the Earth holds a quiet motion that never stops. The ground may seem solid, but deep below, it moves in ways that shape everything we know. The surface of our planet is made of vast slabs of rock called tectonic plates. They drift slowly across the mantle, the layer beneath the crust, carried by heat rising from deep inside the Earth. These plates move only a few inches each year, yet their motion over millions of years has built mountains, opened oceans, and rearranged continents. The world beneath us is never still. It is always rebuilding itself. To understand this, it helps to look back to the beginning. The young Earth was a sphere of molten rock, glowing from the heat of its own formation. The solar system around it was violent, a place of constant collisions. Asteroids struck with enormous force, keeping the surface liquid and unstable. Over time, the planet began to cool. Heavy metals such as iron and nickel sank toward the center, forming the core. Lighter rocks floated upward and slowly hardened into the first crust. It was thin and fragile, broken often by eruptions that poured lava across the surface. Above it, gases from volcanoes formed a thick atmosphere filled with carbon dioxide, methane, and ammonia. There was no oxygen yet, only heat and chemical haze. Even in that fiery age, water found a way. Some of it came from steam that condensed and fell as endless rain. Some was delivered by icy comets that melted on impact. For millions of years, the rain fell onto the still hot crust, hissing and boiling as it touched the rock. Slowly, the first oceans formed, shallow and scattered at first, but spreading as the surface cooled. Those early waters began to carve channels and carry minerals back to the sea. They softened the land and set in motion the slow chemistry that would one day lead to life. From space, the young Earth would not have looked like the planet we know. There were no large continents, no familiar shapes. Instead, small islands of rock floated and merged, forming unstable landmasses that drifted across a molten background. These movements were the first signs of the process we now call plate tectonics, the restless shifting of the crust. The mantle below moved like a slow, thick current, pushing and pulling the surface in great, uneven patterns. Unlike Mars, which cooled and fell silent, or Mercury, which hardened into stillness, Earth remained active. Its crust was thin enough to break. Its mantle stayed hot enough to flow. Its core kept spinning, generating the magnetic field that protects us from solar radiation. These conditions made the planet alive, in a geological sense capable of constant renewal. Mountains would rise, erode, and rise again. Oceans would open, then close. Continents would meet, collide, and separate over and over, shaping the face of the world. The early Earth was both dangerous and generous. Volcanic eruptions filled the sky with ash and gas, and meteor strikes left deep scars. Yet those same processes built the crust that would one day hold life. Water gathered in great basins. The air began to change, slowly clearing. It was a planet searching for balance, a balance that depends not on stillness, but on motion. Heat and pressure worked together like opposing hands, keeping the planet in motion, but within limits. Even the moon played a role. It was born from a massive collision between Earth and a Mars-sized body. The debris from that impact came together in orbit, forming our moon. Its gravity helped steady Earth's tilt and slowed its rotation, keeping our climate more stable. The tides it raised stirred the early seas, mixing minerals and shaping the first shorelines. From the very start, the Earth and Moon moved together, each influencing the other. When we look at the ground today, it feels permanent. Mountains seem fixed, coastlines appear timeless, but that stillness is an illusion. The continents move slowly but steadily, each one riding its tectonic plate across the planet's surface. The speed is barely noticeable, just a few centimeters per year, but across millions of years, that slow drift reshapes everything. The Himalayas, the Andes, the Atlantic Ocean itself, all are products of motion that never stops. At the dawn of the 20th century, scientists believed the Earth was static. They thought continents were fixed in place, and that mountains rose simply as the planet cooled and shrank. It took one curious mind to challenge that picture. Alfred Wegener, a German meteorologist, noticed that the shapes of the continents seemed to fit together like puzzle pieces. The eastern edge of South America matched the western curve of Africa almost perfectly. He wondered if they had once been connected. Wegener collected clues from fossils and rocks. He found that identical plant and animal remains appeared on continents now separated by oceans. The same ancient mountain chains lined up when he rejoined the continents on a map. Evidence of glacial deposits existed in regions that were now tropical. To him, these signs pointed to one conclusion: the continents had once been part of a single landmass. He called it Pangea, all Earth. Over time, Wegener said, this giant continent broke apart, and the pieces drifted to their current positions. It was a bold claim, but he could not explain how such motion was possible. His best idea was that the continents pushed through the ocean floor like icebergs through water. Most geologists found that idea impossible. The Earth's crust, they argued, was too solid for such movement. Wegener's theory was dismissed as fantasy. Some critics mocked him openly, saying his ideas belonged to weathermen, not to serious geology. For decades, the theory of continental drift sat on the edges of science, but the evidence Wegener gathered remained. The puzzle-piece coastlines, the matching fossils, the aligned mountain ranges, all waited quietly for a new explanation. That explanation came in the mid-20th century, when advances in technology allowed scientists to study the ocean floor in detail. After World War II, ships equipped with sonar mapped the seabed and revealed an unexpected landscape. In the middle of the Atlantic ran a long chain of underwater mountains, the Mid-Atlantic Ridge. Similar ridges appeared in other oceans. When scientists examined the volcanic rocks from these regions, they found strange magnetic patterns. The minerals within the rocks aligned with Earth's magnetic field at the time they formed. But Earth's magnetic field had flipped many times over millions of years, with north and south trading places. These reversals left alternating stripes of magnetic polarity across the ocean floor, mirrored on either side of the ridges. This pattern could only mean one thing. New crust was forming at the ridges, pushing older crust outward. The ocean floor itself was spreading. The continents were not plowing through solid rock. They were being carried along as part of larger plates moving on the mantle beneath them. In the 1,960 seconds, these discoveries came together as the theory of plate tectonics. Wegener's idea was reborn, now supported by the physics of mantle convection and the hard data of ocean mapping. Mountains, earthquakes, volcanoes, and ocean trenches could all be explained by the movement of these plates. The once ridiculed concept became the foundation of modern geology. Looking back, it is easy to wonder why so few saw what now feels clear. But that is how science grows through questions that first sound impossible. Wegener never lived to see his theory accepted. He died on an expedition to Greenland in 1930, yet his vision changed how we see the planet. The Earth, once thought solid and unchanging, became a living, moving system. Today, every map of tectonic plates carries part of his legacy. The continents drift, collide, and reshape the planet, just as he imagined. What began as a lonely idea grew into a framework that explains not only the surface of Earth, but also its deep inner workings. The seafloor's magnetic stripes, the chains of volcanoes, and the pattern of earthquakes all tell the same story. Beneath the stillness, the world moves. The invention of plate tectonics was not a single discovery, but a gradual unfolding. It was the slow turning of doubt into evidence, and evidence into understanding. The lesson it leaves is quiet, but lasting. Even in science, truth can take time to rise. What seems uncertain today may one day become the foundation of knowledge. Just as continents drift across the globe, human understanding moves forward, carried by curiosity and patience, always shifting, always alive, beneath the restless Earth. Beneath the continents and oceans, the planet's surface fits together like a puzzle too vast for the eye to see all at once. The ground may seem quiet, but it is made of great slabs of rock tectonic plates, moving slowly across a deep, heated interior. Imagine the Earth as a cracked shell that never stops shifting. Each fragment slides, collides, or separates under the steady pull of heat from within. There are 7 major plates that define most of the surface. The African plate spans deserts, forests, and savannas, stretching outward into the Atlantic. The North American plate carries not only the continent itself, but also the ocean floor that lies east of it. To the South American plate drifts toward the Pacific, where it meets the denser oceanic crust of the Nazca Plate. Across the globe, the Eurasian plate stretches from the Atlantic all the way through Europe and Asia, touching nearly every region of the Northern Hemisphere. Beneath the Pacific lies the largest of them all, the Pacific Plate covering nearly a third of the planet's surface. Around the southern pole sits the Antarctic Plate, turning slowly under its icy weight. To the east, the Indo-Australian Plate moves northward, pressing into Asia and driving the rise of the Himalayas. Around these giants are smaller plates and fragments, shards caught between the main pieces. The Cocos Plate of Central America, the Caribbean Plate, the Philippine Sea Plate, and many others all shift and grind where the larger plates meet. Together, they make a living mosaic, one that never settles into a final shape. Each plate drifts a few centimeters per year, carried by slow currents deep in the mantle. Over a lifetime, that motion is invisible. Over millions of years, it reshapes the planet. Oceans open and close, mountains rise, then wear down. Continents move thousands of miles from where they began. At the edges where plates meet, the real drama unfolds. These boundaries are where the surface is created, destroyed, or rearranged. Geologists describe three main kinds of plate edges: divergent, convergent, and transform boundaries. At divergent boundaries, plates move apart. Molten rock from the mantle rises into the gap, cools, and hardens into new crust. This process creates long mountain chains on the ocean floor called ridges. The Mid-Atlantic Ridge is the most famous and underwater range running down the center of the Atlantic Ocean, where the Americas drift slowly away from Europe and Africa. The process is constant and patient. Each year, the Atlantic widens by only a few centimeters, yet across millions of years, it becomes a vast ocean. At convergent boundaries, plates push toward each other. When a dense oceanic plate meets a lighter continental one, the oceanic plate is forced downward into the mantle in a process called subduction. As it sinks, it melts and fuels volcanoes that rise along the edge of the continent. This is what happens around the Pacific Ring of Fire, a circle of volcanic arcs and deep-sea trenches that marks one of the most active regions on Earth. In other places, when two continents meet, neither gives way. Instead, they fold and crumple, pushing up mountains. The Himalayas are one result, a range born from the collision of the Indian Plate and the Eurasian Plate, a clash still underway today. The third kind of boundary is transform, where plates slide past each other horizontally. Here, the crust is neither created nor destroyed, but the movement builds up stress until it releases in sudden bursts earthquakes. The San Andreas Fault in California is one of these boundaries, where the Pacific Plate moves north along the edge of the North American Plate. Los Angeles and San Francisco creep closer together each year by only the width of a fingernail, yet the tension between them can release with tremendous force. Together, these boundaries form a balanced cycle of renewal. Divergent zones build new crust, convergent zones recycle old crust, and transform zones shift the pieces sideways. Without them, the planet would be motionless and barren. Instead, this restless system keeps Earth young, reshaping its surface and renewing the conditions for life. Along these boundaries, we find the heartbeat of the planet. At mid-ocean ridges, jets of superheated water gush from the seafloor, forming black smokers' chimneys that feed entire ecosystems in the dark. Along subduction zones, deep trenches mark the downward path of old crust, while arcs of volcanoes rise above, their eruptions both destructive and creative. Along transform faults, the tension of the crust is released suddenly, shaking the land above. Every quake, every eruption, every mountain range is part of this same slow machinery. The discovery of plate tectonics tied these once separate events into one elegant idea. Earthquakes, volcanoes, and the building of mountains are not isolated mysteries. They are parts of a single process, driven by heat and motion within the planet. The Earth's surface behaves like a giant puzzle, each piece distinct but connected. When one moves, others respond. The Pacific Plate dives beneath South America, raising the Andes. The African Plate splits apart in East Africa, where a new ocean may someday form. The Antarctic Plate drifts in quiet isolation, surrounded by spreading ridges that keep it turning. Every edge tells a story, and together they form the living history of the planet. Yet, for all we know, much remains hidden. The plates are enormous, moving on timescales too vast for human senses. What seems to us like stillness is, in fact, constant motion. Most of the boundaries where this happens lie beneath oceans or deep within mountains. far from daily view. Still, their effects reach everywhere. The shape of every coastline, the height of every mountain, and even the chemistry of the oceans are the products of these slow shifts. Unlike a finished puzzle, Earth's surface is never complete. There is no final picture. The pieces slide, collide, and fracture endlessly, making new forms and erasing old ones. The puzzle beneath our feet is alive, guided by heat and gravity, and in its slow, ceaseless movement, it reminds us that nothing on this planet is truly fixed, not even the ground itself. Far below the crust lies the true source of this motion, the mantle. Though it cannot be seen, it is the great engine of Earth's restlessness. The mantle is a vast layer of rock, nearly 3,000 kilometers deep. It is not liquid, but under immense pressure and heat it flows slowly, almost like warm wax. Heated from below by the core, it moves in giant currents. Hot material rises, cool material sinks, and the circulation pushes the plates above it. This movement, called convection, is the hidden force behind the drifting continents. The mantle's pace is impossibly slow, centimeters per year, but its reach is global. Over millions of years, it drives every rearrangement of the planet's surface. Sometimes the flow brings up narrow columns of superheated rock called plumes. These plumes burn through the crust, creating fixed points of volcanic activity known as hotspots. As a plate drifts over a hotspot, volcanoes form in a chain. The Hawaiian Islands are one such chain, each island marking where the Pacific Plate once passed above the same plume. Hotspots have shaped continents as well. The vast lava fields of India, known as the Deccan Traps, formed from a massive eruption millions of years ago, perhaps contributing to the extinction of the dinosaurs. In Iceland, a plume rises beneath the mid-Atlantic ridge, keeping the island split and active as new crust forms below it. These features show that the mantle is not uniform but alive, with rising and sinking flows. At mid-ocean ridges, molten rock from the mantle cools into new seafloor, spreading outward as more material rises to replace it. At subduction zones, old crust sinks back down, melts, and becomes part of the mantle once more. It is a conveyor system that has been running for billions of years. Without it, the Earth would lose its power to rebuild. Why does it move so slowly? The answer lies in the balance of forces. The mantle's rock is dense and heavy. Heat from the core rises gently, and gravity resists every motion. The result is a planet-sized tug-of-war where change is constant but never rushed. A plate may shift only a few inches in a lifetime, but across millions of years, that distance becomes thousands of miles. Oceans appear and vanish. Mountains rise and fall. Continents travel from pole to pole, carried by the deep engine below. The mantle's flow is not always steady. Cold slabs of sinking crust can pull plates faster. Hot plumes can speed up volcanic activity, or even split a plate in two. Seismic waves allow scientists to map parts of this hidden world, but much of it remains a mystery. What happens 3,000 kilometers below our feet cannot be seen directly, only inferred through its effects on the surface. Yet from those clues, we know enough to see the pattern. The deep Earth moves, and through that movement, the surface lives. The heat that drives the movement of continents and oceans follows a rhythm both powerful and calm. Deep inside the planet, heat rises from the core, cools, and sinks again, creating a slow cycle that never ends. From that steady flow comes the rearranging of the world, the drift of continents, the birth of oceans, and the building of mountains. The mantle, unseen and silent, is the breath of Earth itself, exhaling through volcanoes, and inhaling as old crust returns to the deep. For all its strength, this engine depends on balance. Too much heat and the crust would tear apart faster than it could heal. Too little, and the planet would freeze into stillness. Our Earth rests in a rare middle ground, restless enough to renew itself, stable enough to sustain life. This balance keeps oceans circulating, climates shifting, and living things adapting across ages. Every landscape we know, the mountain ridge, the rolling plain, the sea floor, exists because of that quiet harmony between fire and stone. Beneath the illusion of stillness, the mantle churns like a tide that never stops. It pushes continents together, pulls them apart, and redraws the map of the world, centimeter by centimeter. That drift may seem trivial on a human timescale, but without it, there would be no Himalayas, no Pacific Ring of Fire, and no Atlantic widening between the Americas and Europe. The engine beneath ensures that Earth is alive, a planet that builds and rebuilds itself endlessly. There are places where this motion reveals itself in striking ways, where the crust is stretched and torn apart by the forces below. Most lie hidden beneath the oceans, but their effects reach across the entire globe. These are the divergent boundaries, the seams where tectonic plates pull away from each other, allowing new crust to rise from the depths. Each boundary marks a place of creation, where molten rock cools into new seafloor. Over millions of years, these zones have reshaped every ocean basin on Earth. The Mid-Atlantic Ridge is the most famous of these seams. It runs like a great scar down the center of the Atlantic Ocean, from the Arctic to the southern seas. Though hidden beneath kilometers of water, it is the longest mountain range on the planet. Its peaks and valleys stretch for tens of thousands of kilometers, home to ecosystems that live in total darkness. Along this ridge, molten rock rises from the mantle to fill the gap as the plates drift apart. When it cools, it forms new crust, which is then pushed outward by newer material rising behind it. In this way, the Atlantic Ocean slowly widens year by year, its floor spreading like a conveyor belt that never stops moving. The rocks nearest the ridge are the youngest on Earth, while those near the edges of the ocean are ancient, having drifted for hundreds of millions of years before sinking again in distant trenches. This steady renewal is what keeps our planet dynamic. Without it, the continents would have remained locked together as they were hundreds of millions of years ago, with no Atlantic between them. The ridge is a reminder that the planet never stops remaking itself. Divergent boundaries exist in every ocean. The East Pacific Rise, the Indian Ocean Ridge, and countless smaller rifts mark where the crust splits and reforms. Together, they form a network of seams longer than all the rivers on Earth combined. Most of these ridges are unseen, mapped only through sonar and the echoes of seismic waves. Yet they are among the most active and creative regions on the planet. Around them, life has found extraordinary ways to survive. Hydrothermal vents spew jets of mineral-rich water heated by magma below, forming clouds that feed entire ecosystems. Giant tube worms, white crabs, and heat-loving bacteria thrive in these places, drawing energy not from sunlight, but from the chemical reactions within the water itself. These dark oases show that life can flourish even in the deepest shadows, sustained by the energy of the Earth's interior. Not all rifts are hidden underwater. In East Africa, the process is happening in plain sight. The East African Rift stretches thousands of kilometers from the Red Sea down through Ethiopia, Kenya, and Tanzania. Here, the African plate is slowly splitting apart. The smaller Somali plate drifts eastward, and the land between them sinks to form deep valleys and lakes. volcanoes rise along the fault lines. Lake Tanganyika and Lake Malawi fill rift valleys that mark the slow tearing of a continent. The Great Rift Valley of Kenya, with its steep cliffs and fertile plains, is a visible reminder that Earth's crust is still opening. Though the movement is too slow to feel, its effects are lasting. Over millions of years, this rift will widen, and seawater will flood the valley. The Horn of Africa may one day stand as an island, separated by a new ocean born from the heart of the continent. Such a transformation seems distant, yet it follows the same pattern that once opened the Atlantic. The patience of the planet works on a scale beyond imagination. Oceans are born, not in explosions, but in whispers, stretched across millions of years. These rifts remind us that continents are not permanent. What seems solid beneath us is only a temporary arrangement. The land we live on is a page in an ongoing story, written not in words, but in the rearrangement of rock and sea. Today's mountains are tomorrow's islands. Today's valleys are the seeds of future oceans. Divergent boundaries may cause quakes and eruptions, but their deeper purpose is renewal. They keep the surface alive, preventing it from falling into stillness. If you could stand on the edge of the East African Rift, you might see small cracks in the ground, quiet signs of a continent in motion. They seem harmless, almost invisible, yet they trace the line where the future ocean will one day flow. If you could return in 10 million years, you would see a shoreline where there is now dry land and waves breaking where grass once grew. The crust breaks not in anger, but in creation, making room for what comes next. Every fracture is both an ending and a beginning. If divergent boundaries are where new crust is born, subduction zones are where old crust returns to the deep. Earth is a master recycler, never letting its surface grow endlessly outward. Instead, the oceanic plates that spread from ridges eventually meet their fate, where they collide with other plates and sink back into the mantle. This process, called subduction, is one of the most powerful and essential forces shaping the planet. Subduction begins when two plates meet head-on. The heavier oceanic crust slides beneath the lighter continental crust, plunging into the mantle. The descent forms a deep trench in the ocean floor, one of the most dramatic features on Earth. The Mariana Trench in the Pacific sinks nearly 11 kilometers below sea level, so deep that Mount Everest could vanish within it. As the plate sinks, friction builds along the contact zone. When that stress releases, the result is an earthquake. Many of the world's most powerful earthquakes begin in subduction zones. The 2011 event off Japan, which unleashed a devastating tsunami, came from a plate sliding beneath another. Similar collisions have shaken Chile, Alaska, and Indonesia. Yet this process is not only about destruction. As the plate descends, it carries water and sediment into the mantle. These materials cause the surrounding rock to melt, forming magma that rises through the crust and erupts as volcanoes. The result is a volcanic arc, a line of peaks that mirror the trench below. The Andes in South America, the Cascades in North America, and the volcanoes of Japan and Indonesia all mark active subduction zones. These arcs are the surface expression of Earth's recycling system. Where crust descends on one side, it re-emerges in fire on the other. Between them, the ground shakes as plates grind and strain. It is a process of destruction and renewal woven into a single cycle. From afar, the life of an oceanic plate might seem short and brutal. Born at a ridge, it drifts across the ocean floor for tens or hundreds of millions of years, only to be pulled downward and melted back into the mantle. Yet this is the rhythm that keeps the planet balanced. Without subduction, new crust would build endlessly at ridges. Oceans would swell, and continents would lose their shape. Subduction ensures that creation and destruction stay in harmony. Evidence of these vanished oceans remains in the rocks. Ancient volcanic arcs have eroded into granite mountain ranges. Pieces of long-lost oceanic crust now lie high in the Himalayas and the Alps, lifted during collisions and preserved as thin layers of dark basalt. Even the air we breathe bears traces of this process. Volcanoes fed by subducting plates release gases that influence the atmosphere: carbon dioxide, water vapor, and sulfur compounds that have helped shape the planet's climate over eons. Though scientists understand much of how subduction works, its beginnings are still debated. Does a plate sink because it grows heavy with age? Or must some other force push it down first? Why do some subduction zones stay active for hundreds of millions of years while others fade away? These questions remind us that the deep Earth still holds mysteries no instrument can fully reach. The timescales involved are staggering. A single plate can take hundreds of millions of years to complete its journey, from its birth at a ridge to its death in a trench. The seafloor beneath us today may one day vanish entirely, melted and reborn elsewhere. Land and sea change places, mountains rise and crumble, and the planet renews itself again and again. To stand above a subduction zone, if it were possible, would be to feel the quiet tension of two immense forces meeting. Beneath the waves, a slab of crust slides downward. Above it, volcanoes rise where that same crust returns to the surface as magma. The ground trembles, the coastline shifts, and mountains slowly build from the pressure. Every movement, from the faintest quake to the fiercest eruption, is part of this grand exchange between surface and deep. Subduction keeps the planet in balance. For every kilometer of crust created at a ridge, another is consumed in a trench. The planet does not grow or shrink, it recycles. The crust is renewed through fire and folded back into the mantle in a continuous loop. When we look at the arcs of volcanoes circling the Pacific, or the long trenches cutting through the ocean floor, we see only the surface of this deeper rhythm. Beneath lies a world of heat and motion that has shaped Earth since its beginning. The continents and oceans we know today are temporary travelers in that cycle. They shift, vanish, and return in new forms over spans of time too vast for human memory. Mountains rise from what was once ocean. Seabeds harden into peaks that scrape the sky. Subduction is not an ending, but a transformation, a way the planet renews itself endlessly. In that slow, steady recycling, the Earth remains alive, changing without haste, creating the future from the remnants of its own past. When continents meet head-on, the result is far from gentle. Unlike the slow slipping of oceanic crust or the quiet parting of a rift, a continental collision is a contest of equals. Neither side is dense enough to sink into the mantle, and neither yields easily. The crust responds by crumpling, folding, and thickening, forcing rock upward until mountain ranges rise across thousands of kilometers. Geologists call this process orogeny, the making of mountains, and it is one of the most dramatic outcomes of plate tectonics. The Himalayas are its most striking example. Around 50 million years ago, the Indian plate, once an isolated landmass south of the equator, began racing northward at a pace unusually fast for a continent about 15 centimeters a year. It crossed the ancient Tethys Ocean and finally collided with the Eurasian plate. The oceanic crust between them vanished, pushed down and melted, and the two continents locked together. With no way for one plate to sink, the rocks were forced upward and the Himalayas were born. Even today, the Indian plate keeps pushing north and the mountains keep rising, growing a few millimeters each year. The highest peaks on Earth, such as Everest and K2, are still climbing, shaped by forces that began long before humans appeared. For climbers, these peaks are a challenge. For geologists, they are living experiments. The collision that raised them continues to this day, and earthquakes ripple through the region as the crust adjusts to the relentless compression. To the people who live there, the mountains are both beautiful and dangerous, magnificent in scale, yet capable of shaking the ground without warning. But orogeny is not limited to Asia. The Alps formed when the African plate pressed northward into Europe, folding and stacking layers of rock into sharp ridges and deep valleys. The older Appalachians of North America tell of an even earlier collision when Africa and North America joined during the assembly of the supercontinent Pangea. Time has softened their outlines into rolling green hills, but their rocks still bear the scars of that ancient impact. In each case, mountains rise where continents refuse to yield. The mechanics of this process are complex, but follow a simple rule. Pressure builds until stone behaves like clay. Layers that once lay flat on the seafloor bend and fold into arches and troughs. Blocks of crust slide over one another like wrinkled fabric pushed from the sides. Great slabs of rock are thrust tens of kilometers from their original positions. Over millions of years, erosion carves these uplifted structures into peaks and valleys. Rivers cut deep channels. Glaciers grind ridges into sharp spines. Wind and rain smooth the debris into fertile plains. Yet even as erosion wears mountains down, the continuing collision lifts them anew. This balance between uplift and erosion keeps mountain ranges alive. The Himalayas rise almost as quickly as weather and water can wear them away. If the collision were to stop, the peaks would eventually crumble into dust and be carried to the sea, as happened to ancient ranges before them. But while the plates still converge, the push upward matches the pull downward, and the mountains endure. They are fragile in form, but eternal in process, a delicate equilibrium between building and wearing away. The impact of continental collision reaches far beyond topography. When mountains rise, they change weather, rivers, and even the chemistry of the air. The uplift of the Himalayas altered global wind patterns, strengthening monsoon systems that feed the Great Plains of India and Southeast Asia. Rain and ice wear down the young peaks, sending vast amounts of sediment into rivers that spread it across floodplains and deltas, creating some of the most fertile soils on Earth. As fresh rock is exposed to the atmosphere, it reacts chemically with carbon dioxide, slowly drawing the gas out of the air and influencing long-term climate. In this way, mountain building helps regulate the planet's temperature over geological time. Every range tells a similar story. The Andes mark a collision between oceanic and continental plates, where subduction and uplift combine. The Alps show how continents fold and buckle under pressure. The Appalachians preserve the memory of an ancient union now long dissolved. Together, they reveal that the surface of the Earth is not a stable crust, but a living record of motion and change. The Himalayas stand out because their collision is still active. The Indian plate continues to push into Asia, compressing a region that stretches thousands of kilometers. Tremors roll through Nepal, Tibet, and northern India as the crust adjusts to the strain. Entire cities sit above the faults that mark this slow-motion crash. For the people who live there, the mountains are a daily presence, majestic, spiritual, but also unpredictable. They remind us that the boundary between beauty and danger is thin, drawn by the same forces that give rise to both. For scientists, mountains are windows into deep time. In the folds and faults of their rocks lie the traces of vanished oceans, long-buried sediments, and ancient climates. Each layer is a chapter of Earth's history, written in minerals and pressure lines. By studying them, geologists can reconstruct how continents moved, how climates shifted, and how life adapted to the changing face of the planet. It is remarkable to realize that something so solid is born of movement. Mountains are monuments to motion, the result of continents drifting, colliding, and reshaping themselves. Their strength comes not from stillness, but from struggle. Over eons they rise, endure, and fade, replaced by new peaks elsewhere as plates continue their slow dance. The Appalachians were once as high as the Himalayas. One day, the Himalayas will be worn down into gentle hills, their sediments spread across the ocean floor to become the foundation of future ranges. Why do they keep rising even now? Because the plates beneath them have not stopped. The mantle still churns, the crust still crumples, and the forces of uplift still exceed the drag of erosion. Mountains are caught in a tug-of-war between gravity pulling down and tectonics pushing up. As long as the upward force wins, the peaks climb higher. Their height is a measure of energy locked in stone, slowly released as time grinds on. The story of colliding continents is therefore one of power and patience. It shows how immense energy, working across millions of years, can shape the surface of a planet. It also shows that the landscapes we admire are temporary, still forming under our feet. When we look at the Himalayas or the Andes, we are seeing a moment in an ongoing transformation, a frozen snapshot of rock in motion. Every ridge, every valley, is part of a continuing dialogue between Earth's inner heat and its outer skin. Eventually, all collisions find their balance. The forces driving uplift weaken, erosion gains ground, and the towering ranges are worn to plains. The sediments carried to the oceans will someday be compressed into new rock and raised again when another set of continents meets. In that sense, mountains never truly die. They are reborn in cycles that span the life of the planet. Yet the story of Earth's motion is not limited to slow building. Sometimes the energy stored in these vast systems releases all at once. While mountain ranges rise quietly over ages, earthquakes announce themselves in seconds. They are the sharp exhalations of a planet that usually breathes slowly. An earthquake begins where stress has built along a fault, a fracture in the crust where two plates or blocks of rock grind against each other. These faults do not slide smoothly. Friction locks them in place, while the forces from the moving mantle continue to push. Over decades or centuries, tension builds until the rock abruptly breaks and slips. The sudden release of energy sends waves rippling through the ground. The first are primary or P waves, compressing and expanding the rock like a pulse through a spring. Next comes secondary or S waves, shaking the earth side to side. Finally, surface waves roll along the crust, causing the most visible motion and damage. In a large quake, the ground can seem to ripple like water, though what moves is solid stone. Earthquakes have reshaped history, as well as landscapes. Lisbon's quake in 1755 leveled much of the city and sparked philosophical debates about fate and nature. The San Francisco quake of 1906 tore open the San Andreas Fault and transformed the understanding of how faults work. Japan's 2011 earthquake, one of the strongest ever recorded, generated a tsunami that crossed the Pacific and altered nuclear policy worldwide. Most earthquakes are much smaller. Thousands occur every day. Their vibrations too faint to feel. Sensitive instruments called seismographs record them, tracing the subtle motions of the crust. Together, they reveal a planet constantly moving, never fully at rest. Prediction remains one of science's hardest challenges. Faults do not follow regular patterns. Some release stress through small slips. Others remain locked for centuries before lurching violently. Scientists can identify zones where large quakes are likely, but not when they will occur. This uncertainty has led engineers to focus on preparation instead. Buildings in quake-prone regions are designed to bend without breaking. Bridges are fitted with dampers and deep foundations. In countries like Japan, networks of sensors can detect the first, faster P waves and send alerts seconds before the stronger waves arrive, enough time to stop trains and warn people to take cover. Despite these precautions, earthquakes remain deeply unsettling. Volcanoes and storms announce themselves. Earthquakes strike without warning. Their suddenness is what makes them so memorable and so humbling. In a few seconds, the ground that seemed stable reminds us it is alive. Yet, earthquakes are not only agents of destruction. Over geological time, they shape landscapes, raising mountains, creating valleys, and redirecting rivers. Some lakes and basins exist solely because quakes warped the crust. Seismic waves from a major quake can travel around the planet several times, ringing it like a bell. By studying how those waves move, scientists can probe the interior of the Earth, mapping the mantle and even the core. In this way, earthquakes are also tools of discovery, natural experiments revealing the structure of our world. They remind us that stillness is an illusion. We live on a surface that shifts and strains even in its calmest moments. To build on such a world is to live in partnership with its motion. The energy that destroys also sustains, keeping the planet active and renewing the conditions for life. Mountains rise, quakes release, and the cycle continues, each event a heartbeat in the long life of Earth. Volcanoes are the planet's open wounds and its healing scars, both destroyer and creator, both furnace and forge. They are the visible mouths of Earth's deep interior vents through which molten rock, gas, and ash rise from the mantle to the surface. To see one erupt is to glimpse the living heart of the planet laid bare. Beneath the crust, pressure builds slowly, heat gathers, and finally the surface gives way. The result can be as gentle as a slow flow of glowing rock, or as violent as an explosion that reshapes entire regions in minutes. The greatest concentration of this volcanic activity circles the Pacific Ocean in a band known as the Ring of Fire. This vast loop runs for more than 40,000 kilometers, from the Andes in South America, up through North America's Cascades, across to Japan and the Philippines, down to Indonesia and New Zealand. It marks the edges of subducting plate zones, where oceanic crust dives into the mantle, melts, and feeds long arcs of volcanoes. More than 3/4 of the world's active volcanoes sit along this fiery boundary, a reminder that the Pacific Plate, though immense, is constantly under siege by its neighbors. Here, the planet's tension is visible in every steaming vent and trembling fault. Not all volcanoes behave alike. Some are broad and low, their slopes stretching wide like the curved surface of a shield. These are shield volcanoes, built by repeated flows of thin, fluid lava that spreads easily across great distances. Their eruptions are steady rather than explosive, forming vast domes of basaltic rock. The Hawaiian Islands are prime examples. Mauna Loa and Kilauea rise gently from the sea, their eruptions painting new land layer by layer. Standing on their slopes, one can watch rivers of molten rock move like slow fire, advancing silently across the dark terrain. Each eruption is a small act of creation, extending the shoreline and reshaping the island's form. Other volcanoes are far more dangerous. Stratovolcanoes, also called composite volcanoes, grow tall and steep from alternating layers of hardened lava, ash, and rock fragments. Their magma is thicker and more viscous, trapping gases until pressure builds beyond containment. When they erupt, the explosion can tear mountains apart. Mount Vesuvius buried Pompeii in ash nearly 2,000 years ago, preserving a city in perfect stillness. Krakatoa's eruption in 1883 shattered the island itself, generating waves that crossed oceans and a sound heard thousands of kilometers away. Mount Street, Helens in 1980 blew sideways, leveling forests and sending a plume of ash that darkened skies for days. These volcanoes can lie quiet for centuries, gathering strength in silence before releasing it in moments of fury. Yet even in their violence, volcanoes are builders. The land beneath our feet owes much of its existence to ancient eruptions. The crust of the oceans was born from lava rising along mid-ocean ridges. Entire continents carry the marks of massive volcanic provinces, regions where colossal eruptions once poured out enough lava to cover countries. The basalt plateaus of India, the Columbia River basalts in the United States, and the Siberian traps are among these immense remnants. Over time, wind and rain turn volcanic rock into soil rich in minerals, some of the most fertile on Earth. The slopes of volcanoes support dense forests and farmlands, their soils renewing with every eruption. People settle near them despite the risks, drawn by both beauty and abundance. Volcanoes also influence the atmosphere. When they erupt, they release carbon dioxide, water vapor, and sulfur dioxide. Over millions of years, this slow outgassing has helped maintain the planet's climate, recycling carbon between the deep mantle, the oceans, and the air. But in short bursts, volcanic activity can alter the balance dramatically. In 1815, the eruption of Mount Tambora in Indonesia threw so much ash into the sky that global temperatures dropped. The following year became known as the Year Without a Summer. Crops failed in Europe and North America. Sunsets turned blood red across the world. Volcanic power reaches far beyond the slopes of a single mountain. It can touch the entire planet. Because they hold both peril and promise, volcanoes have occupied a special place in human thought. Cultures living near them have long woven them into myth and religion. The Hawaiian goddess Pele is said to dwell in the lava of Kilauea. In Japan, Mount Fuji is sacred, a symbol of beauty and endurance. For the ancient Romans, Vulcan, the god of fire, worked his forge beneath volcanic mountains. These stories capture a truth. Science also recognizes volcanoes are the planet's way of breathing, releasing pressure and reshaping itself from within. To scientists, volcanoes are natural laboratories. Each eruption brings material from deep inside the Earth, minerals and gases that reveal the composition of the mantle. By studying them, geologists learn how heat moves through the planet and how tectonic forces drive the motion of continents. The chemistry of volcanic rock provides a record of Earth's interior, offering glimpses of processes we cannot observe directly. In that sense, volcanoes are storytellers, giving voice to the planet's hidden workings. Standing near one, the senses are overwhelmed. The ground hums with vibration. The air smells of sulfur and stone. Gases hiss from vents as molten rock glows through cracks. At night, fountains of lava light the sky, painting the horizon in red and gold. It is a sight of both terror and wonder, proof that the earth beneath us is alive and creative, reshaping itself in real time. Around the ring of fire, this cycle of destruction and renewal never stops. Shield volcanoes in Hawaii and Iceland build new land quietly. Stratovolcanoes in Japan, Indonesia, and the Andes bide their time until pressure breaks their calm. Submarine volcanoes erupt unseen on the ocean floor, creating mountains that may one day rise as islands. The rhythm is constant: eruption, erosion, rebuilding. Volcanoes recycle the crust, release gases that feed the atmosphere, and create the raw materials that sustain ecosystems. They are not accidents of geology, but essential parts of the Earth system, linking the deep mantle to the surface world. From volcanoes, the story of the planet leads naturally into the oceans, where most of the volcanic action takes place unseen. Beneath kilometers of water lies a terrain as complex and dynamic as any on land, a world of mountains, valleys, and deep trenches. The seafloor covers 2/3 of the planet's surface, yet remains less explored than the moon. It is the place where Earth's tectonic machinery is most active and most mysterious. Much of the ocean floor is made of abyssal plains, vast, flat regions that stretch for thousands of kilometers. They are covered with fine sediments that settle slowly over millions of years, creating smooth surfaces that seem eternal. But beneath that, calm lies movement. The crust beneath the abyssal plains is oceanic crust, constantly created at mid-ocean ridges and destroyed in trenches. These plains are the quiet skin of a conveyor belt, sliding slowly toward their fate. In other regions, the ocean floor plunges into deep scars known as trenches. The Mariana Trench in the Western Pacific is the deepest, reaching nearly 11 kilometers below the surface. These trenches mark where one plate sinks beneath another, carrying sediments, seawater, and life itself into the mantle. The pressure is immense, the darkness absolute. Only a handful of human missions have ever reached these depths, yet they are vital parts of the Earth's recycling system, the places where the crust is consumed so that new crust can form elsewhere. Balancing these abysses are the mid-ocean ridges, immense mountain chains that run like seams across every ocean. Together, they stretch more than 60,000 kilometers, forming the longest mountain range on Earth. Along these ridges, plates drift apart, and molten rock rises to form new seafloor. Though hidden in darkness, the ridges glow with heat and activity. If the oceans were drained, they would appear as a continuous mountain system encircling the planet. In the late 1970s, scientists exploring one of these ridges near the Galapagos Islands made a discovery that reshaped our understanding of life. At hydrothermal vents, tall chimneys spewing superheated water, they found entire ecosystems thriving without sunlight. Bacteria there used chemical energy from the vent fluids to produce food, supporting giant tube worms, clams, and shrimp. Life, it turned out, could exist without the sun, drawing energy directly from the chemistry of the Earth. These black smoker communities, may resemble the earliest ecosystems on the planet, formed in the dark safety of the deep ocean while the surface was still hostile. The seafloor holds other records too. As molten rock hardens at ridges, the iron within it aligns with Earth's magnetic field. Over time, the planet's magnetic poles have reversed many times, and each switch leaves a pattern in the rocks, a barcode of magnetic stripes on the ocean floor. By reading these stripes, scientists have traced the history of seafloor spreading and continental drift. The sediments that settle over the crust carry their own stories, layer upon layer of microscopic shells and dust recording changes in climate, ocean chemistry, and even mass extinctions. The seafloor is the Earth's archive, a vast geological library waiting to be read. Despite decades of exploration, much of the ocean floor remains unmapped. Remote sensing and sonar reveal large-scale features, but countless smaller details remain unseen. More people have walked on the moon than have visited the deepest parts of the ocean. Each new expedition finds something unexpected, a new species, a new vent field, a strange geological formation no one predicted. The deep ocean remains a frontier, one that hides as many secrets as the cosmos above. To imagine the seafloor is to imagine a world within a world. Picture wide plains of fine sediment, calm and dark, moving slowly as the crust beneath drifts towards subduction zones. Picture the trenches deep, shadowed scars where the surface of the planet is swallowed whole. Picture the ridges glowing with molten rock and the vents releasing clouds of minerals that sustain life in the black water. Every part of this hidden world tells the same story: creation and destruction intertwined, the constant renewal of the Earth beneath the waves. The ocean floor is not a static foundation, but an active participant in the planet's evolution. It is where the tectonic cycle is most visible, where new crust forms and old crust returns to the deep. It is also where some of the earliest life may have begun, nurtured by warmth and chemical energy rather than sunlight. To explore it is to look into the machinery of the Earth itself, to see how the restless energy of the interior shapes the planet we know. Beneath the waves, Earth continues its ancient work, unseen but unceasing. There, fire meets water, pressure meets depth, and life adapts to both. The seafloor is proof that our planet is not finished. It is still being written, one eruption, one trench, one drifting plate at a time, a living story unfolding in the dark. The continents that shape our maps and frame our sense of home seem immovable. Mountains hold their silhouettes for generations, rivers follow ancient paths, and coastlines appear eternal. Yet every continent, every familiar shape, is only a brief pause in an endless journey. The surface of Earth is a restless mosaic, its pieces drifting, colliding, and breaking apart in a grand rhythm known as the supercontinent cycle, a geological heartbeat that pulses over hundreds of millions of years. Continents are not anchored to one place. They are slow travelers, carried by the churning of the mantle beneath. From time to time, the wandering plates gather into a single massive landmass, a supercontinent, only to be torn apart again as heat builds below. Each cycle leaves behind a new world, new oceans, new climates, new paths for life to follow. The most famous of these ancient unions is Pangea, which formed around 300 million years ago. Its name, meaning all Earth, described it perfectly: a vast supercontinent that stretched from pole to pole, surrounded by one global ocean called Panthalassa. The world of Pangea was both united and divided. Its coasts were rich with forests and wetlands, while its interior baked in arid heat. Far from the sea, the air was dry and the land dusty. shaped by deserts as wide as continents. Early reptiles roamed these plains. Amphibians lingered in shrinking rivers, and the first true dinosaurs took their tentative steps. But Pangea was only the latest chapter. Before it came Gondwana, a supercontinent that dominated the southern hemisphere more than 500 million years ago. Gondwana united what are now South America, Africa, Antarctica, Australia, and India, forming a massive southern landmass fringed by shallow seas. Its breakup would later scatter these pieces across the globe, sending some northward to collide again and build new mountain ranges. And long before Gondwana, there was Rodinia, an ancient supercontinent over 1 billion years old, formed when the planet's first large land masses clustered together in a world without complex life. Each of these supercontinents rose and fell in turn, lasting hundreds of millions of years before heat and motion broke them apart. Around 200 million years ago, Pangea itself began to split. Rifts opened through its center, and lava welled up to form the early Atlantic Ocean. The Americas drifted westward, while Europe and Africa moved east. India broke free and began its long journey north toward Asia, a collision that would one day raise the Himalayas. Australia slid away from Antarctica and wandered into warmer seas. The breakup of Pangea was not chaos, but continuity. The same tectonic forces that once drew the continents together now pulled them apart. At the heart of this process lies the slow convection of the mantle. Heat from Earth's core rises toward the surface, creating vast currents of solid rock moving like syrup over eons. Where these currents converge, plates collide and mountains rise. Where they diverge, rifts open and oceans are born. When a supercontinent forms, it acts like a lid, trapping heat beneath it. Over time, that trapped heat weakens the crust and forces it to crack, beginning the cycle anew. It is an elegant system of balance, creation leading to destruction, destruction leading to creation. Geologists believe the Earth has gone through at least 3 or 4 full supercontinent cycles: Rodinia, Gondwana, Pangea, and perhaps others now lost to erosion and time. Each cycle reshaped the planet's geography, altered its atmosphere, and set new conditions for life. When continents merge, global sea levels tend to fall, exposing wide shelves and reducing the area of shallow coastal seas. When they split apart, the opposite happens. Oceans flood new rift valleys, creating fertile, shallow waters that spark bursts of evolution. The joining and parting of continents have rewritten the story of life many times over. Supercontinent assembly also reshapes climate. A single vast landmass disrupts wind and ocean currents, often creating extremes, dry interiors and stormy coasts, hot deserts beside frozen highlands. When a supercontinent breaks apart, the pieces move to new latitudes, carrying forests, deserts, and ice sheets with them. Global circulation patterns shift, altering rainfall, temperatures, and even atmospheric composition. Entire species rise or vanish depending on how the continents rearrange. The breakup of Pangea, for example, triggered massive volcanic activity along its rifting zones. The gases released during these eruptions likely contributed to one of the largest mass extinctions in Earth's history at the end of the Triassic period. Yet the same events opened new ecological spaces, setting the stage for the dinosaurs' rise. The supercontinent cycle thus governs both creation and extinction, the rise of worlds and their undoing. And this process is far from over. If current motions continue, Earth will one day see another great reunion. scientists call the next possible configuration Pangea Ultima. In this imagined future, perhaps 250 million years from now, the Atlantic Ocean will close as the Americas drift eastward to collide again with Europe and Africa. The Mediterranean will vanish as Africa pushes north into Europe, raising new mountain chains where seas once lay. Australia will join Asia, while Antarctica may drift north toward warmer latitudes. The continents will fuse into a single supercontinent surrounded by a vast global ocean, an Earth both familiar and alien. No humans will be there to witness it, but the process will continue regardless. The planet does not pause for observers. The map we know is temporary, a momentary arrangement in a story billions of years long. The cycle of supercontinents, Rodinia, Gondwana, Pangea, and whatever comes next, reminds us that permanence is an illusion. Mountains rise and fall, oceans open and close, and continents wander endlessly across a stage that never stops shifting. There is a quiet order within this repetition. The Earth remakes itself not through chaos, but through rhythm. Like a tide measured in millions of years, continents come together and drift apart, and in doing so, they set the conditions for everything else: climate, life, even the chemistry of the air. The movement of continents is not only a geological process, it is also a biological one. The slow drift of plates has guided the evolution of life as surely as it has shaped mountains and seas. Beneath all living history lies a foundation of motion. The tectonic engine connects the deep earth to the surface, and the carbon cycle is its messenger. Carbon, the element of life, is traded constantly between rock, air, ocean, and living organisms. Volcanoes, powered by subduction and mantle plumes, release carbon dioxide from the deep mantle. Each eruption and vent adds to the atmosphere, warming the planet and sustaining photosynthesis. But this is only half the story. As mountains rise and their rocks are exposed to rain and air, chemical weathering draws carbon dioxide out of the atmosphere. Rivers carry the dissolved carbon to the sea, where it becomes locked into shells and sediments. Subduction then drags that carbon back into the mantle, where it can stay for millions of years before being exhaled again through volcanic vents. This planetary breathing keeps the climate stable across deep time. Without plate tectonics, carbon would either accumulate endlessly, turning Earth into a furnace like Venus, or be trapped forever, freezing the planet like Mars. The slow exchange between surface and interior keeps the thermostat of the planet balanced. It is a feedback system older than life itself, yet essential to life's survival. Tectonics also guides the rhythm of ice and warmth. When land masses drift toward the poles, ice sheets expand, reflecting sunlight and cooling the planet further. When continents cluster near the equator, warmth dominates and ice retreats. Around 34 million years ago, Antarctica settled into its current position at the southern pole, surrounded by a new circular ocean current that trapped cold water around it. That isolation allowed glaciers to grow, creating the frozen continent we know today. Later, when the Himalayas rose, increased weathering drew carbon from the air and cooled the global climate further, ushering in the long series of ice ages that shaped the modern world. These planetary rearrangements have also written the script for evolution. When continents merge into supercontinents, life converges. Species meet, compete, and sometimes vanish in great extinctions. When continents drift apart, life diverges. Isolated populations evolve into unique forms. Australia, separated from Gondwana, became a sanctuary for marsupials and monotremes. species found nowhere else. South America's long isolation allowed strange creatures like giant ground sloths and terror birds to thrive, until the rising Isthmus of Panama reconnected it with North America 3 million years ago, sparking a great interchange of species. Africa's slow northward drift exposed rift valleys and broad savannas, the landscapes where early humans evolved. Even in the seas, tectonics guides life. The opening of the Atlantic created new coastlines and shallow seas that fueled bursts of marine diversity, while the closing of the Tethys Ocean erased ancient ecosystems forever. Every major shift in evolution echoes a shift in the Earth's crust. The forests we walk through, the deserts we cross, the climates we inhabit, all are products of tectonic motion. Even the soils that nourish crops were born from the erosion of mountains lifted by plate collisions. The quiet movement of continents underlies every breath of air, every drop of water, every form of life. It is humbling to think that the same forces that topple cities with earthquakes or bury valleys in volcanic ash also sustain the conditions for life. The energy that seems destructive in the moment is, over time, creative. The drifting plates regulate temperature, circulate carbon, and redraw the boundaries of ecosystems. They have turned a once barren rock into a world of forests, coral reefs, and civilizations. The timescales are almost beyond imagination. Plates drift only a few centimeters per year, the speed at which fingernails grow, yet in 1,000,000 years, they can shift entire continents. A small nudge northward, and ice sheets advance, a mountain range rises, and the chemistry of the atmosphere changes. An ocean opens, and new species appear. The slow beat of tectonics is the planet's heartbeat, steady and deep, shaping every pattern we see. It is ironic that the most important motions are the quietest. We notice the sudden violence of earthquakes and eruptions, but it is the patient drift of plates that determines the fate of worlds. Plate tectonics is not just the machinery of geology, it is the architect of climate, the partner of evolution, and the unseen sculptor of the living planet. The continents beneath our feet are temporary. The mountains we see are mid-rise, and the air we breathe carries whispers from volcanoes that burned long ago. The ground is not fixed, it moves with purpose. Every shift, every crack, every plume of heat from the deep continues the same story that began billions of years ago. A planet forever shaping and reshaping itself, keeping life in balance, and reminding us that even the solid Earth is a living, moving thing. The rocks beneath our feet are not silent. They are pages in an unending chronicle, each layer preserving a trace of how the world once was. Every fossil, mineral vein, and grain of sediment is a record of motion of heat, pressure, water, and time working together to write Earth's autobiography in stone. The oldest pages lie deep below, written in languages only geology can read. Among the clearest voices in this record are fossils. They are not merely relics of creatures long gone, but evidence of the planet's own shifting design. A fossilized leaf or bone can reveal where continents once touched, how climates shifted, and when entire ecosystems rose and vanished. Fossils are time travelers. They bridge continents, linking places now divided by oceans and millions of years. One of the most telling examples is a small reptile called Mesosaurus. It lived about 270 million years ago, swimming in freshwater lakes and rivers across what is now South America and Southern Africa. Fossils of this animal have been found on both continents but nowhere else. A freshwater reptile could not have crossed an ocean. which means the two landmasses must once have been joined. At that time, they were part of the southern supercontinent Gondwana, a single, sweeping land of forests, deserts, and inland seas. When the Atlantic Ocean later opened, it tore Gondwana apart, leaving the same fossils stranded on distant shores. Another witness to this ancient unity is Glossopteris, a fern-like tree that flourished across Gondwana more than 250 million years ago. Its fossils have been discovered in India, Africa, South America, Australia, and Antarctica. Today, these regions lie in very different climates, some tropical, some icy, but the spread of Glossopteris reveals they were once connected, sharing a single temperate landscape. Its leaves and seeds are like a green fingerprint pressed across the southern hemisphere, a botanical signature of the planet's wandering crust. Dinosaurs, too, left their evidence in stone. Fossils of large carnivores like Allosaurus in North America have close relatives in Africa and Europe, hinting at open migration routes during the Jurassic period. Long-necked sauropods left their tracks on multiple continents: South America, Africa, and India footsteps that once crossed continuous plains but are now separated by oceans. The fossil record shows not isolation but movement, animals roaming across lands that later drifted apart. Even the landscapes of ancient forests tell the same story. Coal beds in North America, Europe, and Asia preserve the remains of vast carboniferous swamps that once ringed the equator when those continents were joined. Similar deposits appear in China and Siberia, connecting distant lands into one lush, humid belt. These seams of carbon are more than fuel. They are a map of a vanished world. Perhaps the most striking proof comes from Antarctica, a place we think of as endless ice. Beneath its glaciers lie the remains of warm, temperate forests, complete with tree trunks, leaves, and spores. Fossils of reptiles and amphibians also rest beneath the ice, creatures that could not have survived the polar cold. These discoveries make sense only if Antarctica once lay much farther north, still attached to the other continents of Gondwana. The frozen desert we see today was once green and alive before tectonic drift carried it into deep freeze. Smaller fossils add their own details. Tiny marsupials link South America to Antarctica and Australia, showing how mammals once migrated across connected lands. Freshwater amphibians that could never survive saltwater appear in fossils on opposite sides of ancient oceans. Even microscopic organisms, plankton, foraminifera, pollen preserve clues in their patterns of distribution, marking the drift of seas and the turn of climates. When Alfred Wegener proposed the theory of continental drift in the early 20th century, fossils formed one of his strongest lines of evidence. Maps alone could be dismissed as coincidence, but identical fossils of plants and animals on continents now divided by oceans could not. Critics of Wegener could not explain how a freshwater reptile might have crossed the Atlantic, or how identical fern species thrived in both India and Antarctica. The fossils spoke for the continents themselves, testifying that they had once been one. Fossils, though silent, tell stories of movement and transformation. They record the moments when drifting continents tore apart ecosystems, isolating populations and forcing evolution along new paths. They capture the aftermath of collisions that brought species into contact again, mingling and competing in reshaped environments. Each fossil marks an intersection of biology and geology, a record not just of a creature's life, but of the land that carried it. Through them, we see how the planet's restlessness shapes life. When continents drift, climates shift. When mountains rise, rain patterns change. When oceans open, new currents circulate nutrients and heat. Life responds, adapting, migrating, or perishing. The fossil record captures these responses in exquisite detail. Shells that thicken as seas cool, leaves that change shape with humidity, skeletons that evolve for new habitats. Every bone and leaf is a reaction to tectonic motion. To hold a fossil is to hold a memory of a living world now vanished. It may be the impression of a fern that grew in the shadow of Gondwana's glaciers, or the bone of a reptile that swam in a lake now buried under sand. Fossils connect us not only to ancient creatures, but to the moving ground that shaped their fate. They are the breadcrumbs of the continent's long journey, scattered across oceans and eras, leading back to the unity of the Earth itself. Far from the continents, in the silent blue of the open ocean, other traces of Earth's motion rise above the waves. Long strings of volcanic islands arc across the seas, marking where the crust has passed over deep sources of heat. These are hotspots, plumes of molten rock that pierce the mantle and burn slowly through the moving plates above. The Hawaiian Islands are the clearest example. They form a chain stretching thousands of kilometers across the Pacific. At the southeastern end lies the Big Island, still alive with volcanic fire. Lava flows from Kilauea and Mauna Loa pour into the ocean, cooling instantly into black rock and building new land inch by inch. Moving northwest along the chain, each island grows older, its volcanoes extinct, its slopes softened by rain and time. Beyond them, the chain dives beneath the sea into the Emperor Seamounts, a trail of submerged peaks that record the Pacific Plate's path for more than 80 million years. This line of islands is a geological timeline. Each volcano marks the position of the Pacific Plate at the moment it passed over the stationary hotspot. About 50 million years ago, the line bends sharply, showing where the entire plate changed direction. That kink is a date stamped in basalt, a permanent record of how the surface of the planet reorganized itself. Hotspots are not confined to Hawaii. Iceland, sitting astride the mid-Atlantic ridge, combines a spreading center with a deep plume, making it one of the most volcanically active places on Earth. The Galapagos Islands off South America's coast, the Canary Islands near Africa, and Réunion in the Indian Ocean all owe their existence to hotspots burning through drifting plates. Each is a small, vivid expression of the Earth's inner heat, a fixed flame beneath a moving lid. Volcanic island arcs, by contrast, form not from stationary plumes, but from the collisions of plates. When an oceanic plate subducts beneath another, melting rock rises in a line of volcanoes that trace the edge of the trench below. The Aleutian Islands of Alaska, the Marianas of the Western Pacific, and the Lesser Antilles in the Caribbean are born of this process. Each arc mirrors the curve of the subduction zone beneath it, a graceful sweep of peaks marking where one plate dives under another. Island arcs and hotspot chains differ in origin, yet both reveal the same truth. The planet is alive with motion. Arcs are created by destruction, crust sinking and melting, while hotspots are born from creation, magma rising and building new land. Together, they maintain the balance of the Earth's surface. Over geological time, island arcs have done more than trace the boundaries of plates. They have helped build the continents themselves. When arcs collide with larger landmasses, their volcanic roots can weld onto them, adding new crust piece by piece. Much of the continental edges we see today began as ancient arcs fused onto older cores. The continents, it turns out, are mosaics assembled from countless island fragments carried by moving plates. Despite their violent origins, volcanic islands often become havens of life. Hawaii's slopes support dense rainforests and coral reefs nourished by volcanic minerals. Iceland's stark lava fields host mosses and seabirds that thrive in the cool North Atlantic. Even barren arcs like the Aleutians become nesting grounds for vast colonies of seabirds. Life finds a foothold wherever new land emerges, turning volcanic ash into soil and stone into shelter. Yet these islands, too, are temporary. As the crust beneath them cools and sinks, they slowly subside. Waves erode their coasts, wind softens their peaks, and over millions of years, they vanish beneath the ocean. The emperor seamounts were once islands like Hawaii, but now they sleep far below the surface, their volcanic hearts long cold. Island arcs also drift and change shape as subduction zones migrate. The islands we know today are just brief chapters in an ongoing cycle of creation and disappearance. Each chain of islands is a sentence in the language of plate tectonics. Hotspot trails are dotted lines, spelling out the slow drift of plates. Arcs are seams stitched across oceans where new crust is forged and old crust consumed. Both reveal motion, invisible to the human eye, but undeniable when traced through deep time. To stand on a volcanic island is to stand on the newest crust of the planet. Beneath your feet lies rock that was once liquid fire, raised from the mantle and cooled in the open air. Around you stretch oceans whose floors are older than the land you stand upon. Look down the chain of islands, and you see time itself laid out a record of motion, of drift, of the quiet persistence of the planet's heat. Islands are fleeting, yet their story is enduring. They remind us that Earth is constantly remaking itself, filling its oceans with markers of change. Each island, whether born of a hotspot or a subduction arc, is a testament to the planet's creativity. They rise from fire, gather life, and slowly return to the sea. In their birth and their erosion lies the rhythm of the world itself, patient, steady, and endlessly in motion. For most of human history, the earth beneath our feet was something to be trusted. It gave us ground to stand on, soil to grow food, stone to build with. It seemed permanent, unmoving, solid, and yet every so often it reminded us, otherwise shaking, cracking, or erupting with fire. Those moments of upheaval carved deep marks, not just in the land, but in the human imagination. Long before science offered explanations, people turned to story. Myth became a way to describe a planet that would not stay still. In Japan, the quakes that shattered villages and split the ground were said to come from Namazu, a giant catfish that lived deep beneath the islands. The god Kashima was said to pin it down with a heavy stone, but when his grip slipped, Namazu thrashed, and the land trembled. Even centuries later, prints of the great fish appear in old artwork, symbols of both chaos and awe. The story carried truth in its own way, an image of energy held in check beneath the surface, waiting for release. Across the sea in ancient Greece, the earth's movements were ruled by Poseidon, god of the sea, and the earth shaker. His trident could stir both water and land, bringing quakes and waves in a single gesture. In a world still unmeasured by instruments, such power made sense. When the ground shook, it was a god speaking. It was divine anger or warning. The planet itself, alive with intention. In Italy, Mount Etna was said to be the forge of Hephaestus, the god of fire and metalwork. The mountain's eruptions were his sparks, the thunder of explosions, his hammer striking anvils deep underground. In Polynesia, the fiery goddess Pele carved the Hawaiian Islands with her lava flows, her temper creating new land even as it destroyed the old. Worshippers brought offerings to her craters, honoring both the danger and the gift of living on volcanic soil. Far to the north, Norse legends gave the trembling ground another face. Loki, the trickster god, was said to be chained in the depths of the earth, venom dripping onto his skin. When he twisted in pain, the land shook, sending tremors through Midgard, the realm of humans. Even in frozen lands where volcanoes were rare, the idea of a living, restless earth persisted, a being bound, angry, and breathing beneath the rock. These myths were not simply fear made into story. They were reflections of balance. Fire could destroy but also create. Quakes could bring ruin, but also shape new landscapes. People living near volcanoes knew the fertile richness of ash-filled soil. Those along fault lines built traditions around respect for the ground's power. Myth was a language of coexistence, a way to live with danger through reverence rather than denial. Across cultures, the stories shared common roots. In Chile, the Mapuche people spoke of two serpents locked in struggle, Kai Kai, ruler of the seas, and Tren Tren, guardian of the land. Their battles caused earthquakes, floods, and the rising and sinking of mountains. Along the Pacific coast of North America, indigenous tales told of the thunderbird, whose wings beat against the air in battle, with great sea creatures shaking the earth in their clashes. The imagery changed with each land, but the insight was the same. The planet was alive, and its unrest was the pulse of something larger than human understanding. As centuries passed, these myths shaped how people responded to disaster. Offerings were made, rituals performed, temples built on mountainsides, not only to worship, but to acknowledge that the earth's power was shared, not owned. Myths gave fear a form and turned chaos into meaning. When the ground cracked or the mountain burned, it was not random. It was a story playing out, a warning, a punishment, a renewal. Even as the age of science dawned, the search for meaning continued. In 17th and 18th century Europe, earthquakes were still seen as divine messages. The Lisbon earthquake of 1755 shattered not only buildings, but beliefs. It struck during morning mass on a religious holiday, toppling churches and sending a tsunami through the city. Tens of thousands died. The devastation forced philosophers and theologians to ask why. Some said it was punishment for sin. Others said it was a test of faith. But for the first time, voices also rose, asking whether natural forces, not divine ones, could explain such destruction. That debate became one of the sparks of modern geology. Science did not erase the wonder, it redirected it. As instruments replaced stories, humanity began to listen to the earth in new ways. The trembling that once signaled a god's anger became a clue to hidden layers beneath us. The smoke that once marked a forge of deities became evidence of heat flowing from the mantle. The same impulse to explain, to connect, remained only now. It worked through observation and measurement instead of myth and prayer. Among the tools that reshaped our understanding was the seismograph. At first glance, it is simple. A heavy mass suspended so that when the ground shakes, the pen it holds traces a wavy line on paper. But when networks of seismographs spread across the globe, they became a kind of planetary sensor. an X-ray machine for the Earth. Every earthquake sends out waves that travel through the crust and mantle, bending and slowing depending on what they pass through. By studying those waves, geologists can map the interior of the planet, tracing where cold slabs of crust sink into the mantle or where plumes of hot rock rise. Even the core, once a mystery, revealed its structure through the way seismic waves echoed within it. Earthquakes, while destructive, have become tools of discovery. Each tremor, each ripple of energy, tells scientists how the planet is built. A quake in Japan can reveal the density of rock beneath Africa. A jolt in Chile can whisper clues about the boundary between core and mantle. The Earth speaks through vibration, and technology has learned to listen. Another key to understanding comes from the sky. Global Positioning System satellites built to guide ships and cars also serve as millimeter-precise trackers of tectonic motion. Arrays of receivers planted across continents record how the ground itself shifts year by year. In California, GPS stations show the Pacific Plate sliding northward past North America along the San Andreas Fault. In the Himalayas, they capture India's steady push into Asia, the slow collision still lifting Everest a few millimeters each year. These movements are imperceptible to the eye, but satellites see them clearly. They chart the quiet drift of continents, proving that even the most ancient mountains are not fixed monuments, but works in progress. The same tools that map a morning commute also measure the breathing of a planet. Satellites offer even more. Radar interferometry, a method of comparing radar images taken from orbit at different times, can detect how the ground shifts after an earthquake or volcanic eruption. A single eruption in Chile or a quake in Turkey can move the land by centimeters, and from hundreds of kilometers above, satellites can see it. By layering images taken days or weeks apart, scientists create color-coded maps showing exactly how the ground deformed. This view helps predict where strain is building and where the next event might occur. It's as if the entire crust has become a living topographic map, its motions visible frame by frame. The oceans, though, remain the hardest place to study. Most of the planet's tectonic boundaries lie hidden under kilometers of water. There, seismometers rest quietly on the seafloor, recording rumbles no human can feel. Underwater robots explore hydrothermal vents, sampling minerals and tracking the chemistry of water heated by magma. Submersibles descend into deep trenches, mapping slopes where one plate slides beneath another. These instruments bring back data from places darker than any cave, deeper than any mine, where the story of tectonics unfolds, unseen. Instruments now measure what myths once imagined. Where ancestors pictured catfish and serpents, we see subduction zones and mantle plumes. Where they spoke of gods striking the earth, we detect seismic waves spreading through layered rock. Yet the human instinct behind both is the same: to understand the world's motion, to find pattern in its chaos. Even in the age of satellites and supercomputers, the Earth retains its mystery. Instruments can describe the movement, but they do not erase the wonder, the tremor underfoot, the hiss of a volcano, the slow drift of continents. All carry echoes of something ancient in us, a reminder that the solid ground is part of a living whole. Science and myth, in their own ways, share a purpose. Myth turned fear into story. Science turns curiosity into knowledge. Both are ways of listening to the planet, to ourselves, to the long rhythm of motion that ties them together. Each generation builds better tools, but the impulse remains unchanged: to watch, to measure, to make sense of the trembling earth, and in doing so, to remember that stillness has always been an illusion. Even with satellites in orbit, sensors buried in rock, and computers simulating the flow of the mantle, the Earth still guards its secrets closely. The deeper we look, the more intricate the picture becomes. What truly drives the motion of tectonic plates remains one of geology's great unanswered questions. The general outline is clear enough. Heat from Earth's core rises through the mantle, setting up slow convection currents that drag the crust above. Yet the details, how those currents form, how they shift, how they interact, are full of debate. Some researchers picture narrow plumes of hot rock rising like columns from the deep mantle, feeding volcanoes such as those in Hawaii or Iceland. Others think the upwellings are broader and more chaotic, shaped by turbulence in the slowly moving rock. The same uncertainty surrounds the downward motion of slabs sinking into the mantle. Do they stir the flow like paddles, folding and mixing as they descend? Or do they slip quietly into deeper layers, melting and disappearing into the mantle's vast interior? Even the birth of a subduction zone is a mystery. Once a plate begins to sink, gravity keeps it moving, pulling the rest of the plate down behind it. But what starts that first plunge? Some scientists suggest that heavy oceanic crust eventually grows unstable and folds under its own weight. Others think collisions or rifting elsewhere in the plate network push it down. Without knowing how subduction begins, we cannot fully explain how the entire tectonic engine started billions of years ago. Earthquakes and volcanoes, though better understood than in past centuries, still refuse to give up their full predictability. We can estimate which faults are ready to break and which volcanoes are under pressure, but the exact timing remains hidden. Stress builds slowly, then releases without clear warning. Volcanoes can slumber for centuries and erupt suddenly despite quiet readings the day before. The planet keeps its schedule secret, revealing it only in bursts of fire or trembling ground. Looking backward is no easier. The evidence of early tectonics is faint and fragmentary. The oldest rocks on Earth, more than 4 billion years old, have been reworked again and again by heat and pressure. Clues to the planet's early behavior are blurred, like words written on paper and then erased. Scientists suspect that the young Earth, still hot from its formation, may have behaved differently. Its crust, perhaps locked in place under a stagnant lid, unable to break into plates. Over time, as the mantle cooled and the crust thickened, the first cracks may have appeared, creating small, shifting fragments that evolved into the plate system we know today. Understanding the transition is crucial because it connects to how continents formed, how oceans emerged, and how life found stable ground to begin its long story. But the record is sparse. Only tiny outcrops in Greenland, Canada, and Western Australia preserve the oldest hints of crust. They hold chemical fingerprints suggesting the recycling of material, perhaps the earliest echo of plate motion, but nothing definite. The beginnings of tectonics remain one of science's quiet frontiers, a puzzle still missing its opening piece. While the past is clouded, the future also stretches before us in uncertain outlines. We know the continents are still drifting. We can measure Africa moving northward, Australia sliding northeast, and the Atlantic widening by centimeters each year. But the ultimate destinations remain uncertain. One day, the pieces will gather again into another supercontinent, just as Pangea once did. But where and how it will form is still a matter of imagination. Some models show the Atlantic beginning to close as new subduction zones form along its margins, pulling the Americas back toward Europe and Africa. In this version of the story, called Pangea Ultima, the continents reunite into one vast landmass, surrounded by a single ocean. Other scenarios envision a northern union, with the continents drifting toward the Arctic to form a Pangea. Still others picture a reunion across the Pacific, a supercontinent named Novo Pangea. Each simulation traces millions of years of motion, but none can be called final. The plates move according to forces too complex to predict so far ahead. Whatever shape the next supercontinent takes, the consequences will be profound. When continents cluster together, they reshape the planet's climate system. Vast interiors, far from the moderating influence of the sea, grow arid and extreme. Winds shift, ocean currents reroute, and rainfall patterns change. Coasts may flourish in narrow, fertile bands, while central deserts expand. The global carbon cycle will adjust, as mountain building and erosion alter the balance of gases in the air. Ice sheets may grow or vanish depending on how the land lies near the poles. The pattern is as old as the planet. Each supercontinent brings a new climate regime. Some eras become frozen icehouse worlds. Others turn into humid, greenhouse ages. These changes unfold over millions of years, but they leave enduring marks. Fossils of tropical plants found in what are now polar regions. Glacial scars discovered in ancient deserts. The position of land determines the temperament of the planet. Africa's slow northward drift is already reshaping the Mediterranean. The sea is narrowing as the African plate presses into Europe. In 10 or 20 million years, the ocean may vanish entirely, squeezed upward into a belt of mountains, stretching from Spain through Greece to Turkey. The collision could rival the scale of the Himalayas, raising new peaks across southern Europe. Farther south, the East African rift is widening, splitting the continent in two. Someday, seawater will flood in, forming a new ocean that divides the Somali plate from the rest of Africa. Meanwhile, the Pacific Ocean, the largest on Earth, shrinks each year as plates subduct around its rim. The Ring of Fire, now known for its earthquakes and volcanoes, may one day close completely, merging Asia with the Americas. The Atlantic, for now, continues to widen, but over hundreds of millions of years, that too could change. Oceans open and close in cycles, breathing in and out across geologic time. New mountain chains will rise where collisions occur. The Himalayas, already the tallest in the world, still climb millimeter by millimeter as India continues its push into Asia. Their glaciers feed the great rivers of the continent, shaping the lives of billions. In the far future, new ranges will appear elsewhere across Europe, in the Pacific, and along the coasts of the next supercontinent. Each range will create new weather patterns, new habitats, and new pathways for erosion that recycle the crust once more. The shifting of land and sea will remake ecosystems as well. Continents moving into new latitudes will carry forests and deserts with them. Species will adapt, migrate, or vanish as climates evolve. Life will respond, just as it always has, following the geography written by tectonics. The planet's restlessness will remain the ultimate designer, sculpting not only the surface, but the story of everything living upon it. For humanity, this movement is both distant and intimate. Distant because the changes unfold on scales beyond any civilization's lifespan. Intimate because we live daily on the results. Mountains rise under our feet, earthquakes test our cities, volcanoes fertilize our fields. Civilizations come and go in the blink of a geological eye. while the continents drift only centimeters in that same time. Yet we are the first species to understand the motion, to measure it, to map it, to see it not as myth, but as process. We know that the Mediterranean's calm waters are the remnants of an ocean being closed. We know that the rift in East Africa is the birth cry of a new sea. We can watch with instruments as India presses into Asia, as California slides north, as the sea floor spreads along mid-ocean ridges. The story, once hidden in myth, is now visible in data, written in numbers and satellites instead of legend and stone. Still, the knowledge does not make the planet less wondrous. The ground beneath us continues its slow, silent rearrangement. We have learned to measure its motion to the millimeter, but not to command it. We can record every tremor, trace every plume, yet the deeper causes remain partly beyond reach. There is beauty in that mystery. The Earth keeps some of its secrets, reminding us that even in an age of precision, not everything can be known. The continents we stand on are temporary. Their shapes will vanish, their mountains will crumble, their seas will open and close again. But the forces behind them, the heat, the pressure, the steady breathing of the mantle will endure. The story of tectonics is not one of completion, but of continuation. The map of the world has never been final, and it never will be. The planet moves beneath us, still, quietly writing its next chapter in stone. Our understanding of plate tectonics has changed not only how we see the planet, but how we see ourselves upon it. For most of history, people imagined Earth as a fixed world, a stable stage where life unfolded. But now we know the stage itself moves, reshaping the scenery as the story continues. The continents drift, collide, and part again. The mountains we climb are still rising. The oceans we sail are still spreading. The ground beneath us is not permanent foundation, but living motion, slow beyond sight, yet constant in its rhythm. In that realization lies both wonder and humility. The science of tectonics does more than describe mechanics. It reveals a planet alive with energy, its deep heart still warm, its surface ever renewed. And within that grand movement, humanity has begun to leave its own faint mark. Our cities, our quarries, our mines and dams, even our carbon in the air, all are signs of a species shaping the surface faster than nature once did. Geologists call this potential epoch the Anthropocene, the age of humans. It is a new layer in the Earth's story, one written not by magma or pressure, but by choice and consequence. For the first time, life itself has become a geological force. Our industry moves more soil and rock each year than all the world's rivers combined. Our gases alter the atmosphere that guides wind and weather. Our dams reshape rivers, our mines hollow hills, our emissions add a chemical signature that future geologists may one day trace in stone. In this way, we have joined the restless Earth not only as witnesses, but as participants, co-authors of a chapter that may be brief but unmistakable. The planet will outlast us, but for now, our hands are on its surface. We know the rules of its motion, that plates drift, that subduction recycles crust, that heat from below drives it all. Yet in knowing, we are reminded of scale. Human history is a flicker compared to the slow heartbeat of geology. The Himalayas have been climbing for 50 million years and will continue long after our cities are forgotten. Oceans open and close over spans longer than all of civilization combined. Even the ground underfoot, the same ground that feels so steady, moves a few centimeters each year, carrying us into a future we can measure but will never see. Still, there is something deeply reassuring about the steadiness of that motion. The continents wander, but not aimlessly. They follow the patient cycles that have shaped the planet for billions of years. Mountains rise and erode, oceans widen and close, climates shift and balance. Each change seems vast, yet it fits within a long pattern that keeps Earth both dynamic and alive. To watch this process unfold, even in glimpses, is to witness a kind of patience beyond human measure. Perhaps that is why the study of tectonics feels more than scientific. It feels philosophical. It reminds us that permanence is an illusion, that everything built, even in stone, is temporary. Empires crumble, but so do mountain ranges. The Earth itself teaches perspective, that change is not disorder, but the engine of renewal. In the collision of continents and the birth of volcanoes, we see the same rhythm that sustains life, destruction, and creation woven together in time. When we look far ahead, the map of the world dissolves into possibility. Africa will press into Europe, closing the Mediterranean. The Americas may one day meet Asia, folding the Pacific into mountains. New oceans will open where today there are deserts. The shapes of continents will be strange and unrecognizable. Humanity will likely be gone, but the planet will continue to write. Its sentences are slow, its punctuation marks measured in earthquakes and eruptions, its paragraphs written in layers of rock. We live in one line of that long book, brief, bright, and fragile. Yet in our short time, we have learned to read what was once hidden. We can see the plates drift in real time, trace the scars of vanished oceans, and map the mantle's deep currents through vibration alone. We have learned to translate the language of stone, to understand what it means when the earth trembles or exhales fire. Knowledge does not still the motion, but it deepens the connection. Time moves differently for the planet than it does for us. What feels eternal to humanity is barely a pause in the Earth's tempo. Mountains rise by millimeters, while rivers carve valleys by grains of sand. The surface we know is a slow-motion tide, always rearranging itself. Our part in this story may be small, but it is not meaningless. To recognize the planet's restlessness is to see the beauty of patience creation stretched across eons, change written in silence. Tectonics is not only a force of geology, it is the memory of the world. Every ridge, every basin, every fossilized shell in the high desert is a trace of motion, the record of collisions and separations older than life itself. The continents carry their pasts with them, sliding like pages across the table of time. When we study them, we are reading an autobiography written by the planet in the only script it knows: pressure, heat, and time. And so the story continues, slow and sure. Continents drift onward, mountains climb and crumble, volcanoes rise, sleep, and rise again. Oceans open, swallow land, and one day give it back. The ground we stand on is not still. It is simply moving too slowly for us to see. Yet if we listen in the deep rumble of an earthquake, in the quiet hiss of magma beneath a mountain, in the steady pull of a GPS reading, we can hear the rhythm of the world itself. The earth is restless, but not reckless. It moves with purpose, with patience, with the calm persistence of deep time. To live upon it is to share that rhythm for a moment, to be carried on a surface that is forever becoming. And as we walk its shifting ground, perhaps the most enduring lesson it offers is this: change is not the end of things, but the way the world endures. The planet will keep moving, silent, steady, and alive long after our names are dust. In its motion, it will remember us, just as it remembers everything, in the layers of rock, in the patterns of sediment, in the traces we leave behind. And somewhere, far in the future, when the continents have joined again beneath a different sky, that quiet record will still tell the story of a living Earth, patient beyond measure, writing itself anew in the slow language of stone.